While many countries are still using trains from the last century, Japan has created machines that look like they came straight out of the future.
Whenever we see a train moving along the tracks, we have no idea that a silent and highly precise engineering system is operating beneath it. Steel wheels glide along rails, transporting thousands of tons of weight across cities, mountains, deserts, and entire continents, often at speeds exceeding 300 kilometers per hour. At first glance, the railway system seems simple. Two rails, a set of wheels, and a vehicle moving forward in a straight line. But this apparent simplicity hides one of the most efficient mechanical solutions ever created in transportation engineering. Unlike cars, trains do not have steering wheels. They do not have differential gears to adjust the rotation of each wheel in curves, and the driver cannot actively guide the train left or right to keep it centered on the track. Once the train is on the rails, the system must guide itself automatically and remain stable under heavy loads and high speeds. Yet trains move safely through long curves, maintain stability at high speed, and remain perfectly aligned with the rails for thousands of kilometers. This stability depends on a small but extremely important engineering detail: the conical shape of train wheels. Train wheels are not flat. They are slightly tapered, forming a subtle cone shape that allows the entire railway system to function efficiently. This small geometric variation is responsible for guiding the train, stabilizing its movement, reducing mechanical wear, and allowing it to turn naturally without complex steering systems. But how does this system actually work in real engineering conditions? Is the same principle used in modern high-speed trains? Would independent rotating wheels reduce wear and friction? And why are train wheels still made primarily of steel instead of lighter and stronger alloys? To answer these questions, we need to understand the engineering logic behind one of the most important components in railway history. The railway system faces a fundamental mechanical challenge. A train must move forward while remaining precisely aligned with the rails, handle curves, vibrations, track irregularities, and heavy loads, and do all of this while maintaining stability and safety. The wheels of a train are rigidly connected by a solid axle. This means both wheels rotate at exactly the same speed at all times. In road vehicles, this would create an immediate problem. When a car enters a curve, the outer wheel travels a longer distance than the inner wheel. To compensate for this difference, cars use a differential system that allows each wheel to rotate at a different speed. Trains do not use a differential. Instead, they rely on geometry and physics to solve this problem in a much simpler and more reliable way. Train wheels are slightly conical, meaning the diameter of the wheel changes from the inner side to the outer side. The outer portion of the wheel has a slightly larger diameter, while the inner portion has a slightly smaller diameter. When the train moves in a straight line, both wheels touch the rails at the same diameter and rotate evenly. But when the train enters a curve, the wheel set naturally shifts slightly toward one side of the track due to centrifugal force and track geometry. As this shift occurs, the outer wheel begins to run on a larger diameter, while the inner wheel runs on a smaller diameter. Because both wheels are connected by the same axle, the difference in diameter automatically creates a difference in distance traveled. This allows the train to turn smoothly, without slipping, without mechanical differentials, and without electronic control systems. The entire process happens naturally through the interaction between wheel shape and rail geometry. It is a simple and elegant engineering solution. One of the most important advantages of conical wheels is the self-centering effect. When the wheel set moves away from the center of the track, the difference in diameter creates a restoring force that pushes it back toward the center. This natural correction keeps the train aligned with the rails and reduces lateral movement. Engineers refer to this behavior as dynamic stability. Dynamic stability reduces vibration, improves passenger comfort, and increases safety. It ensures that the train remains stable even at high speeds and under heavy loads. This is one of the key reasons why railway transportation is considered extremely safe and reliable worldwide. Many people believe that the flange is what keeps the train on the track. The flange is the vertical lip located on the inner side of the wheel. In reality, the flange is mainly a safety feature. Under normal conditions, the flange does not touch the rail at all. The primary guidance comes from the conical shape of the wheels and the contact between wheel and rail. The flange only makes contact in tight curves, irregular track conditions, switches, or emergency situations. Its purpose is to prevent derailment if the wheel moves too far from the center. This means the real guidance system of a train is the conical geometry of the wheels, not the flange. Early railway wheels in the 19th century were made of iron and had very simple profiles. As trains became heavier and faster, engineers began to notice excessive wear, vibration, and instability. Over time, engineers refined the geometry of the wheels and improved materials. Steel replaced iron, manufacturing processes became more precise, and standardized wheel profiles were developed. By the 20th century, railway engineering had established optimized wheel and rail geometries that allowed trains to operate safely over long distances with minimal maintenance. Today, wheel design is based on advanced computer simulations, laboratory testing, and real operational data collected from railway networks around the world. Now, if you enjoy engineering explained in a clear and realistic way, take a moment to support the channel. Leave a like, subscribe to Rail Tech World, activate the notification bell so you don't miss the next episodes, and share your thoughts in the comments. Your support helps us continue creating high-quality engineering documentaries. One of the most common questions is whether high-speed trains use the same conical wheel system. The answer is yes. High-speed trains still rely on the same fundamental principle of conical wheel geometry. However, the level of precision required is much higher. At speeds above 300 kilometers per hour, even small instabilities can become dangerous. Engineers must carefully design the wheel profile to minimize oscillations known as hunting motion, which is a lateral vibration that can occur at high speeds. To control this effect, engineers optimize wheel geometry, rail inclination, suspension systems, and contact forces between wheel and rail. Advanced materials and precise manufacturing allow high-speed trains to remain stable and safe, even under extreme operating conditions. Another interesting engineering question is whether wheels could rotate independently using bearings. In theory, independent wheels would allow each wheel to rotate at a different speed in curves, reducing friction and wear. This concept is similar to the differential system used in cars. However, this would eliminate the natural self-centering effect provided by conical wheels and solid axles. Without this effect, the train would lose stability and require complex electronic control systems to remain aligned with the track. Some tram and metro systems experiment with independent wheel sets, but for heavy freight trains and high-speed rail, solid axles remain the safest and most reliable solution. Another common question is why train wheels are still made primarily of steel instead of lighter and stronger alloys. Train wheels operate under extreme mechanical conditions. They must support enormous weight, resist friction, handle high temperatures generated by braking, and endure millions of contact cycles with the rails. Steel provides the best balance between strength, durability, fatigue resistance, and cost. Lighter materials such as aluminum or titanium may reduce weight, but they wear faster and are significantly more expensive. Modern railway wheels already use advanced steel alloys with carefully controlled chemical composition and heat treatment processes designed to resist cracks, deformation, and long-term fatigue. For now, steel remains the most efficient and reliable material for railway wheels. Modern railway systems use advanced monitoring technologies to ensure wheel performance and safety. Sensors detect vibration patterns, temperature changes, and structural stress. Maintenance machines reshape worn wheels to restore the correct profile and extend their operational life. Engineers continuously analyze data to improve performance and reduce maintenance costs. This combination of traditional mechanical engineering and modern digital technology keeps railway systems operating efficiently and safely around the world. The conical shape of train wheels may look like a small detail, but it is one of the most important engineering solutions ever developed in transportation. It allows trains to turn naturally, stay centered on the track, reduce wear, and operate safely at high speed. From early steam locomotives to modern high-speed rail systems, the same principle continues to guide railway engineering. A simple geometric idea that quietly supports one of the largest transportation systems on the planet every single day.